Hello, this is Brad Strebig, and in this section we're going to talk about what happens to acids in the environment, how they can degrade the environment, but also how engineers and scientists can look at that process, understand the acidification process, and remediate or restore the area that's impacted by that acid conditions. In this case, we're going to look particularly at acid mine drainage, and in Chapter 5, we'll talk about acid rain, which can be remediated in much the same way. One of the most common processes for acid to get into the environment is through the acid emissions of sulfur dioxide and some nitrogen oxides into the atmosphere. Both nitrogen oxides and sulfur dioxide can create localized acid rain conditions where we have high concentrations of the sulfur and nitrogen gases in the atmosphere that dissolve into the raindrops. But in this case, because the sulfur concentrations and nitrogen oxide concentrations, if high enough, can actually decrease the pH of the rainfall. The rainfall falls onto the ground in forms of precipitation. This acid rain then can kill plant life, pollute rivers and streams, and erode stonework, masonry, and other architectural details such as monuments. Acid deposition is formed most significantly from sulfuric acid, from sulfur dioxides emitted from combustion processes. The process of conversion is that we have two sulfur oxide molecules react with oxygen and some particulate matter in the atmosphere to form two SO3 in the air. The SO3 dissolves in solution or reacts with water to form the sulfuric acid H2SO4 in solution. The nitric acid formation is a little bit more complicated, where we have NO2 reaction with a hydroxyl radical in solution plus some metal catalyst to form nitric acid HNO3 in solution. And in the evening, the nitrogen oxide can react with ozone to form the nitrate. This can form N2O5, which also can dissolve in water to form two nitric acid molecules. The acid rain, then, containing extra H+ and numerous anions such as sulfates, ammonia, nitrates, carbon dioxide, or carbonates, and chlorine in the air, can come in contact with the soil. This can result in humic decay, decaying the soil itself, and decreasing or leaching some of the minerals in the soil, such as lowering the availability of calcium by reacting with limestone in solution, changing the pH of aluminum that dissociates to aluminum and other compounds that may inhibit plant growth, and removing other positive metal ions from the environment. About 47% of sulfur dioxide emissions are due generally to power emissions in the Midwest. These weather patterns transport the sulfur oxides into the northeastern states and has led to acidification of lakes and streams that were not buffered by naturally occurring minerals, especially limestones. This has led to a decline in plant and aquatic diversity in many of the northeast U.S. lakes and rivers, and can substantially increase the concentration of dissolved, heavy, and potentially toxic metals in these waterways as well. Here we see a topographic map of pH in the U.S., where we have the highest regions occurring in the mid-Atlantic states, Pennsylvania, New York, and parts of Maryland and West Virginia, where the pH has been logged as less than 4.3 for acidic rainfall. In the western parts of the country, there are some regions where we have some acidic rainfall, but largely limited to the Midwest, and as the wind carries those currents from the coal-fired power plants towards the northeast. In addition, acid rain can interfere with plants themselves, eroding cuticle wax, causing increased evapotranspiration and drying out, and injuring portions of the trees and leaves themselves. It can increase the acidity of the soil and change the natural plants that would be there. It may deplete minerals such as magnesium, potassium, requiring that additional fertilizers be placed, which will have other downstream effects that are negative on waterways that will be discussed in the next chapter in Chapter 4. It can also increase the concentration of mercury and cadmium in lake waters. The good news is that sulfur emissions, since the passage of the Clean Air Act and further amendments in 1991, have decreased substantially over the last 20 or 30 years. We see in the early 1990s the tons per generating unit of sulfur dioxide concentrations actually going down, even though, and this is very important as we discuss sustainability, this graph, notice, the number of generation units is going up, but the concentration and emissions of sulfur dioxides and nitrogen oxides from generating units between 1995 and 2008 was steadily decreasing, leading to less acid gas production. Once rainfall hits, we said that this could mobilize other compounds in the soil. This is especially true where we have surface mining. Surface mining, as we see, can expose various strata, differential strata, here shown as Lexington B, Lexington A, Pikes Gully, so different geologic formations in the earth. These different geologic formations are made up of different minerals that can react differently to changing pH and precipitation. Here we see a surface mine, and we see a farm downhill from that surface mine, so that those mine tailings can contaminate agricultural practices in other areas downhill from the places where the mining is occurring due to exposure of naturally occurring minerals and sediments. One such place is in Elk County, Pennsylvania. This is actually a state game lands called the Dents Run ecosystem. Here we see a map of Pennsylvania, lower right-hand quadrant of that slide, and the outlines of the watershed for Dents Run. In that watershed, there was an open pit mine, and that open pit mine led to acidification of Dents Run and other streams in this area, which degraded the natural ecosystem. This is an area in Elk County which elk have been released and are trying to be reintroduced to the area to increase what was many hundreds of years ago a naturally occurring elk herd, but now is limited mostly to a few northern states and Pennsylvania. Recently, though, elk have also been reintroduced to parts of West Virginia and Virginia as well to further diversify the environment and create more biodiversity in these regions. Prior to mining, as rain fell, it would filter through the soil, perhaps reading some sulfides, but going into the groundwater and being largely diluted, with most of the rainfall going off as surface runoff. However, after mining, surface mining, we see that we can expose those underlying sulfides to the environmental rainfall. These sulfides can then be transported along with surface runoff or reach the groundwater much more quickly than they would have otherwise reached the groundwater by having to filter through the soil. This can result in sulfuric acid formation, just like acid gas formation, which increases heavy metals in the stream, and those heavy metals can result in fish kills. We see here, prior to 2010, so the concentration of hydrogen ions in several streams in the Dents Run watershed. Several of the pHs, Porcupine Run headwaters for instance, are as low as a pH of 2.9, an incredibly acidic condition for a naturally occurring environment. This is due to the acid mine drainage from open mines that existed in this region upstream. So we can see very far upstream in the northern reaches of the watershed, uphill from the mine, the pH was close to a natural level of 6.6 or 6.3, which in this area of the country was fairly good. As we move downstream, however, due to acid acidification, the pH was reduced drastically, down to as low as 3.3 and 2.9 in different areas of Porcupine Run in this watershed. This acid was neutralized, so the pH was measured, the amount of acid was determined, and then calcium carbonate and other acid-neutralizing compounds were put into the watershed upstream of Porcupine Run, where the water would infiltrate into the mines but have to go through an acid-neutralizing section or pond. We see prior to 2010, There was no neutralizing capacity present, so we had very low pH. After the neutralizing capacity was added to Dents Run and Porcupine Run area, we had an increase of pH from 2.9 to 6.55 at several areas along the way. This region of 6.6 is tolerable for most fish species and decreases the amount of hazardous metals also that leach into the stream. Here we see a picture of this Porcupine Run. The red color of the water, this is truly a red color of the water, is red from the dissolved minerals and dissolved metals in the solution that can reach such a high concentration because at acidic conditions, those metals become very soluble. At less acidic conditions, they remain in the soil and do not go into the water or the aqueous phase. The combination of the low pH and the high metal concentration is toxic to a large number of species and will decrease the biodiversity of this area. In this picture, we see a before and after picture of the vegetation in the area as well. So prior to revegetation and neutralization, this area was relatively unvegetated, allowing the surface vegetation to occur, not to occur, and runoff to occur very quickly. On the right-hand side, we see after the neutralization process has occurred, vegetation was replanted and allowed to reform to further decrease the amount of surface runoff from these sulfated and potentially acid mine drainage producing soils. In the very bottom graph, we actually see in this area some of the native elk herd actually bathing in this neutralized pond near Porcupine Run, where the pH is conducive to fresh water and greater biodiversity in the area, both cleaning up the area to make it more aesthetically pleasing, but also increase the biodiversity, actually enhancing the biodiversity, bringing back elk and other species that had not been present since the beginning, perhaps of the Industrial Revolution, and other fish species that may have been degraded through the acid rain emissions from the 1950s, 60s, and 70s. Unfortunately, the United States is not the only area that uses large amounts of coal and produces large amounts of sulfur emissions. China, as well as other countries that use large amounts of coal, also can have similar problems for acid gas emissions, and we see similar problems in the coal burning regions of China, where we have high emissions of sulfur oxides producing very low natural pH levels in waterways that can lead to very many of the same environmental impacts that were discussed in the Northeast United States. In summary, if we understand the chemistry of resource use, waste, and environmental impacts, this understanding can allow us to lead to transformations of degradation processes to neutralize acid conditions and reverse the environmental impacts so that not only we have preservation, but increasing biodiversity of previously endangered ecosystems.